Hey, howdy everyone. So we have already covered many concepts around statistics, probability theory, regression, hypothesis testing, geostatistics. We provided a bit of a context. And many times we had to be very somewhat shallow. We couldn't go into depth because we have to cover a lot of topics in this class. But now I think we're adequately prepared to start talking about concepts around machine. So let's go ahead and get into machine learning. So first of all, for the purpose of this lecture and the next actually 2 lectures, I will be relying on this book quite a bit. An Introduction to Statistical Learning with Applications in R, James and al. Just a great book, great read. I completely recommend it. Go through the first couple of chapters for a lot of the fundamentals. It's really helpful, and it's great to get started. Of course, it's more of a summarization of a much more deep theoretical book that you could also look up and try to work with. So, statistical learning would be a set of tools for learning from data based on some initial assumptions, hypotheses that you may hold with regard to the form of the data or the behavior of the data, or what would be a reasonable model of the data. That would be a general definition that many would recognize. Machine learning versus statistical learning, some would suggest that it's a set of tools for learning patterns. It has very little prior assumptions about what's going on in the data. The whole point is that it is flexible enough that it actually adjusts or adapts to the data. Now, I want to make a note here that many consider statistical learning or machine learning to really be the same, and that this definition I just gave, or this distinguishing between the definitions, is held by some but not by all. And in fact, you'll notice that the book, in fact, is an introduction to statistical learning, but it still covers many of what people would consider to be standard machine learning type of approaches. I like the term statistical learning because I believe that machine learning should not be employed without sound statistical knowledge. And I also feel that the approaches of machine learning really are a natural continuation for what we do with statistical methodologies, and by using that term, we don't forget that. There are 2 types of ways that we can use machine learning or statistical learning approaches. We could work in a supervised manner or unsupervised manner. If we're working in a supervised learning type of manner, then we're trying to build a predictive model for estimating an output given one or more possible inputs. Unsupervised, it's like everything's an input. We have a bunch of different features we're working with, variables, but it's not like we have an output. It's like we're doing a y equals fx, or y is equal to function of x, where x is a bunch of different variables, but we don't have a y. We don't have a specific output. And so what we're trying to do is just learn about the structures directly from the data alone without concern about trying to make a prediction of something with it. Now, also to put machine learning into context, let's talk about the idea of artificial intelligence. And so artificial intelligence, of course, has been around for a long time. And this is this whole idea of theory and developments of computer systems that can perform the tasks that normally require human intelligence. Visual perception, speech recognition, decision making, translation between languages. There's so many, of course this definition came from Google Dictionary, but there are so many different types of ways that we could think about trying to build a system that mimics what people can do. Now, machine learning is really a subset of that. So if we had a bit of a Venn diagram here, we'd have artificial intelligence, and then within it we could have machine learning. It's an application of artificial intelligence that provides systems that are with the ability to automatically learn and improve from experience. They learn without being explicitly programmed. So they look at the data and they learn from the data and they do meaningful things from the data. Now, there's of course deep learning might be a subset of machine learning, and we talk about this as a subset of machine learning for unsupervised learning from unstructured, unlabeled data and so forth. And of course, there's many other types of terms and concepts, but I think this provides us a little bit of context, at least with regard to the concept of artificial intelligence, which has been around for a long time. I specifically like this definition from Wikipedia for machine learning, and let's just go through it. study of algorithms and mathematical models that computer systems use to progressively improve their performance on a specific task. Learning algorithms build a mathematical model of sample data known as training data in order to make predictions or decisions without being explicitly programmed to perform the task. So what are the basic concepts we can distill from this definition? Well, first of all, it's a set of algorithms and mathematical models, so it's a toolkit. It's not just one single type of approach. The other thing, too, is that it is progressively improving its performance on a specific task, so it is learning. And how is it learning? It's learning from sample data known as training data. So it has to be trained with data. An important concept here is that these tools within the toolkit are quite general. They are not being explicitly programmed to perform a specific task. They're a general methodology or model that's flexible enough to be able to attack a wide variety of different tasks. I think there's a really good cautionary note that we should take at the very end of that definition from Wikipedia. It says, they are used where it is infeasible to develop an algorithm of specific instructions for performing the task. The concept is that machine learning is best used in those cases for which we are unable to solve the problem using engineering, science, we don't know the theory, and so that's where it's very powerful. One thing we've got to be concerned about is where we start looking at machine learning as a panacea solution that we're going to use it on every possible problem. No, it turns out that if we know the engineering, if we do a good job of sampling data, we can get a more accurate solution using engineering and science. But at the same time, machine learning will be quite useful for the purpose of solving a lot of problems we don't know the theory, that we're not able to solve through some type of expression. And maybe there's times when speed is more important than accuracy, and machine learning may provide us with something we can use. Well, now there's ethical concerns, and this is where I do a bit of I acknowledge that I'm an engineering professor. I read books, I'm interested in all kinds of topics, but I will not specifically teach on ethics because it's not an area of expertise. I should be honest about that. And so let me just mention a couple of issues, but I'm not going to dive in at all. Ethical concerns. The first one is that you could have bias in the training data. If there's bias in the training data, it is a case of garbage in, garbage out, that the machine will be trained on that bias data, and the bias will be propagated through the system. And so there's a great article, which is the authors are provided here, and we have the link here to it on the archive. It's available. Check it out. So what they did was they actually took pictures of Alaskan Huskies, which I have to say, a beautiful dog right here. And they took those Alaskan Huskies and they mixed it in with wolves. So you had Alaskan Huskies, wolves, 20 pictures, 20 images, and they trained a regression classifier to try to come out with an output. An output would be dog or wolf. Two possible outputs, or two possible outcomes, I should say. Okay. And so what they did was they created a bias in the data set on purpose. They put the wolves all in snow, which, let's face it, most good wolf pictures are in snow. They often are, right? And they put the Alaskan Huskies not in snow. And so then when it came time to actually test their model, they put in a picture of an Alaskan Husky, clearly a very nice example of Alaskan Husky, but not a wolf. And it came back, the model said wolf. Then what they did is they looked at the algorithm and interrogated and found out which cells within the image were used in order to inform that classification. And when they did that, they found that these are the cells that showed up. In other words, it was a wolf because it was in snow. Now, what's the problem here? The problem is that interpretability is often pretty low, or may be low with a lot of machine learning methodologies. It may not be something we can do readily, or we may not take the time to try to interpret and understand why we got the outcome wolf. We may just say this must be a wolf. The application of the machine learning methodologies will likely become routine and trusted. When something becomes routine and trusted, it becomes an authority. And when it's an authority, if you stand up against it and you try to question the result, it often becomes an issue within an organization. Now, I told you I wasn't going to get political or ethical about anything. I'm just saying that there can be bias in the inputs. We may not understand how the decision is made, and we may trust the decision, and it can lead to all kinds of consequences. Now, there are of course, other ethical concerns around machine learning. One is the issue around power. There's a new ability to do rapid inference on very large data sets, and more data is being shared from everybody. I'm on Twitter and Facebook, and I put way too much on, I'm sure, and so we can be concerned about how that's being used. I won't go any further. There's going to be trade-offs in maximizing an objective function, and those trade-offs may be ignored. When we work with typical types of methodologies, models that are simpler, we may understand and see the trade-offs, but we may not see that within the machine in machine learning. And so that can be, and then there's of course societal changes. I won't get into this, but there are likely to be job disruptions. Perhaps there are certain jobs which will be readily replaced by machine learning types of methodologies. And so I won't get into that. Or I think I'm going to make a couple of comments later about it. Big data. So that's kind of my kind of initial discussion about machine learning. Whenever we talk about machine learning, let's talk about big data too, because they're often paired. So what is big data? Well, the general accepted definition is the V's. You have big data if you have enough of these V's. Volume, velocity, variety, variability, and veracity. So, if you have volume. Now, I've been to a data science or machine learning type of meetup, and one of the statements from a participant on a panel was, it's not big data unless it doesn't fit on your laptop. I don't know if that's the right answer. I think a large number of samples, large memory requirements, difficult to visualize is good enough. Another V is velocity. The data is gathered at a high rate, continuously related to the decision cycles. In other words, you've got to make fast choices. The data keeps coming in, you've got to keep making choices, and so that would be velocity. You've got to do something with the data as it's coming. You've got to be able to update. Variety. The data comes from various sources. You have various types, you have different scales, you're having to deal with a variety of different variables. Variability. Data acquisition changes during the project. This often happens in the subsurface. We have seismic information where it was at a certain scale, and then suddenly you have refined and you improved your acquisition method. Now you have higher resolution. There might be different types of error to mitigate and so forth. It changes. And veracity. The data has various levels of accuracy, and we have that all over the place. In fact, let me just make a comment about volume. I would suggest that there are many cases, if you consider recent surveys, seismic surveys in the Gulf of Mexico, CCG's type surveys, where the type of data that they have transmitted through their network in order to support that, we're starting to compete with NASA, with Google, when we're talking about the types of transmission levels. You also think about trying to work with that type of seismic information, pre-stack information with very high resolutions, tons of different attributes and metadata to consider. These are very complicated data sets to consider. When it comes to velocity too, I know people will say in general, unless you're working in smart fields, we don't typically have that kind of real-time thing going. We also have, well, we have smart fields and we have information while drilling and so forth, yes. But at the same time, what I'd suggest, even though our data collection may be punctuated, given the scales that we work with, the decisions we have to make, the complexities of our numerics, I do feel that it's continuous related to our decision cycles. That we still have to make choices every month or two about drilling, where we're going to put our resources in, how we're going to prioritize the development, and so forth. And we have to make those huge decisions at a time when data is being gathered continuously relative to that decision cycle, I would say. So what I'd say is that given all of that, and those arguments, we have variety and veracity and variability too, that energy has been big data, I think long before tech even started thinking about big data because it was being collected online and from other sources. I think us in energy, I think a lot of people working in all kinds of imaging, remote sensing, and so forth, we've been doing things with big data for a long time. Okay, so big data analytics is a method to explore and detect patterns, trends, and to find other useful information from big data in order to improve decision making. I've said this many times before, and I'll say it again. If what you do doesn't impact a decision, then it does not add value. And so it has to impact some type of decision. So let me just draw and put up a little bit of a Venn diagram here and make a comment, and I hope it reinforces some important concepts here. First, we know the definition of statistics. We already covered that a long time ago. We're experts now. Is collecting, organizing, interpreting data, as well as drawing conclusions and making decisions. We always have to make a decision. Geostats, I'm proud of that. It's spatial geologic context. It's stats that accounts for that, the spatial relationships and volume support. And of course, we account for uncertainty, which is always present for us. Ubiquitous, in fact. Big data analytics could be defined as the process of examining large and varied data sets, big data, to discover patterns and make decisions. And what I draw your attention to is, for me, the big data analytics definition is really just the statistics definition. So what would we say? Big data analytics is just using statistics on big data. So we got big data, statistics, and this whole area would be big data analytics to me. Now, what I'd suggest then, that spatial big data analytics, where we're accounting for the spatial context, as geostats does, is the overlap of big data and geostatistics. And so what am I trying to say here? Well, first and foremost, if you're going to do big data analytics, and if we're talking about machine learning before, we should understand statistics. And secondly, if you're going to do that, and you are working with spatial context, I think that we need to understand geostatistics too. Now, I said I wasn't going to be political or anything, but of course, if we're talking about a brand new technology that has a lot of attention, we should remember the hype cycle. And so, of course, the hype cycle has been published before. People have seen it many times before. And of course, you have time versus visibility, attention paid to the technology. And so you have some type of kickoff. There's a peak of inflated expectations, followed by a trough of disillusionment. There's a slope of enlightenment and a plateau of productivity where we get back to something reasonable. We start being productive with the technology, maybe understanding its true value in a more realistic, objective manner. And so clearly we're at a point in this hype cycle. And I think the first comment I'll make is that this is not the first cycle with regard to this technology. There's been other waves before of excitement around AI, machine learning type technologies. And of course, I would say we're probably pretty high, near the peak. And so just as far as we listen to all the messages coming out in communication, I think it's probably wise to kind of learn from the history of technology development and realize that there is the possibility that we may be headed for a trough at some point, of course. Okay, applications around you, societal impacts. Well, if I talk about machine learning and I'm just focused as subsurface and so forth, we are kind of missing some of the more fascinating and amazing things that are going on. And so, of course, driving directions. Everybody's using that now. And I think we've reached a point where most of us are losing our ability to navigate. I'm kidding. Okay, maybe. Air traffic routing to optimize for all the types of constraints as far as flow and fuel usage and all that. Spam filters, thank you very much. Plagiarism checkers, I guess thank you too, being a professor. And translation, computer reading, that's getting really good. Credit card fraud detection. You'll find that if you go purchase jewelry and then immediately buy gas, you might find out that your credit card will be stopped because that turns out that that's a pattern that indicates your card may have been stolen. Face recognition and so more. So recommendations that keep coming up. Apparently, YouTube knows what I want to listen to before I do. Okay, I'm not going to make any jokes there. I just wish sometimes it would kind of like give me diversity, like give me things I haven't seen, because it might be good for me to kind of see new things and hear new things rather than just keep hearing the same music all the time or whatever it might be. Okay, and smart personal assistants. I think I make a comment around, okay, I do here. Okay, so let's just make a couple more comments. We'll get down to some theory here right away. So what are we doing? What is machine learning good at? Well, better utilize data to improve decision making with consistency and with speed. So what's the possible applications to energy? Well, feature detection. guided interpretation. When you're working with dense data sets like seismic or smart field information, being able to rapidly find patterns and say, this is where you should look, or this is what we can interpret, this is where you should focus because this is hard, while the rest of it was easy for a machine to do. Something like that can be very useful. Optimization of field development decisions. Where do you drill? How do you flow it? So forth. What's going on the subsurface? Some type of optimization methods to get the best recovery from the field. Exploration prioritization and fast proxies for forecasting. I have a PhD student who just finished some really good work on that. So now I meet people in tech who suggest that energy is kind of like, like radiology, and it's images. We're looking for just, cysts and so forth, or maybe it's like what Google's doing. I would like to say that I think energy is different than a lot of other fields and is unique. And so has unique challenges that we should consider in the application of machine learning. First, sparse and highly uncertain data. And so what does that mean? It means that there's a pretty thick layer of interpretation required on all of our methodologies. I've seen a variety of tech type groups go into energy companies and say, just give us your data. We're going to do this. And then what I think they're not recognizing is that there is the need for that interpretation, the kind of qualitative assessments that go along with the data. So complicated heterogeneous systems, massive systems, sparsely and uncertain too, sparsely sampled, uncertain. High degree of irreversible interpretation, engineering, physics. And so just getting back on that interpretation again, we know the physics and the science behind a lot of things we're dealing with. There's high uncertainty in sparse sampling, sure. But we know that, and so we have that additional information I think we must always incorporate, we should incorporate. And we have very expensive decisions that must be supported. We're making billion-dollar development decisions, and we have to understand how those decisions are being made. And so this is not YouTube telling me that I want to listen once again to the luminaires again while I'm working for the nth time. No, these are very important decisions being made. And so we have to recognize it's something that we need to have good support for those decisions. Okay, just like spatial statistics, geostatistics, statistical learning is a set of tools. And so you can add this to your toolbox as an engineer. In fact, I'll say I visit a lot of energy companies, and what I'm finding is that they want engineers to know about these tools. There's a huge drive for that. We have an initiative within our department. I'm teaching a brand new machine learning course next fall, and it's all to meet this demand. And so, of course, yes, put this in your toolbox. Just like coding, I'm just saying, learn some coding. Wow, that was angry. I'm sorry, I shouldn't be angry when I record on YouTube. I should save that for my classrooms when I get kind of a little bit, Anyway, so each is very dangerous as a black box. Geostats, machine learning, whatever the method is. You need to understand what's going on under the hood. And so this is where I make an honest acknowledgement right now. I'm new to machine learning too. And so you'll see I'm progressing and learning the technology. I have I have a much stronger background, of course, in geostatistics and data analytics and statistics. And so I'm learning machine learning too. And so I'll just say that up front. And so you'll see I'll teach fundamental basic methods like principal components analysis and also decision trees and so forth. But I'm also growing my capabilities too. And let me just say that. So I will resist the tendency to use things as a black box, and I'll try to build up from my understanding as I go. The methods, the workflows, the assumptions, the limitations, the scope and trade-offs between alternative methods, you have to understand that. Yeah, it's very dangerous if you don't, because you'll just misuse it. So I love this example, and I want to give credit to Clayton Deutsch. This was something that we put together in the book, and I really like it. I think Clayton actually had this idea, and we kind of ran with it. Is imagine you're a carpenter. And if you were a carpenter, you would have a toolbox, just like we as engineers and geoscientists have our toolbox of tools. And you would understand or know each tool perfectly well. And you would understand their performance over a variety of applications, working with different types of wood, different problems you're trying to solve with the tool. What are you trying to accomplish with the tool? My grandfather, when he passed away, he gave his tools to my twin brother, Dave. And I looked at those tools, and what was amazing was after, 50, 60 years of, working with those types of tools, and And they were machine tools. He was a machinist, like my brother is, which is very cool, working with metal. You look at the tools and you could see grandfather's hand in the handles. Over tens of years, he had shaped those tools with his hands. He knew those tools perfectly well. He knew how they behaved when he worked with metal and when he did things with those tools. He would understand the range of applications, the weakness, the strengths, the limits. He would be an expert in their use. He would make choices between tools based on expert judgment and circumstances and goals of the project. You would choose one that you're ready to use. If you were to build a toolkit, you would choose to put in the toolkit the tools that you need to have ready to use. Now, there might be other tools that would be rare. Ones that maybe you weren't more familiar with. You probably wouldn't have them in your toolkit. You have them back in the shop. And because if you had too many tools in your toolkit, your box is overwhelmed with a bunch of obscure tools. And if you have too few tools in your toolkit ready to go, you're not going to be much of a practitioner. You're not ready to solve a wide range of problems. And so there'd be a trade-off. I think myself personally, my journey to learn about different technologies, I want to be like my grandfather and really understand the tools I'm working with. And let's see if I can live up to that. Okay, so, wow, that was kind of deep. That was deep. I hope that was kind of useful to people. Okay, I hope you're motivated. See the potential benefit. Let's get into basic concepts. I got a little more poetic than usual, so sorry about that. So let's talk about the problem. So we have predictors. They're also known as independent variables. They're features. They're in our input variables. And so we imagine that our machine is simply a model of y is equal to a function of x1 through xm. That would mean that x1 through xm are going to be our predictors that we're trying to work with. We have m variables that we're trying to work with. And we'll note that there will be an error term often within our models. We account for the fact that we don't perfectly fit our information. There's error. Response or dependent variables, that's the output variable. And so for that model, again, y is the output. And there could be one or there could be many outputs. That's okay, but we'll just generally show one output. So statistical machine learning is all about estimating that function f. We want to learn that function. And there's two purposes for that. There's prediction and inference. So let's talk about what prediction is. Prediction is estimating that function. So we put hat on that function because it's an estimate. We don't know what's the exact function. That would be kind of arrogant. And we'll just admit that it's an estimate of it. And it's for the purpose of making estimates of y. And that's y hat because it's an estimate. In the geostat context, we often did y asterisk. Or that was our z asterisk was the way we denoted an estimate. And we're focused on getting the most accurate estimates of y. We may not even understand what is happening with our method. In fact, what I should say there is we don't maybe understand all of the interactions in between the variables. We don't understand. We're really focused in prediction on understanding the relationship between x and y. So we're really not. We may not even understand what is happening with regard to, all of the x's with the x's and their relationships with each other between the x's, right? There, that's better. Between the x's. And so accuracy of y hat depends on reducible and irreducible error. Now we acknowledge that f hat is not a perfect model error due to the fact that it's an estimate of it. And so there's going to be components that are reducible and irreducible. But even if we had f perfectly, prediction would still have some error. And that's because of the fact that we could have like the world expert in a specific technology. Andrew Ning or someone could show up here and just like help us build our neural net. And it's the very best neural net we could ever build. But at the same time, we would still have a component of error that is irreducible. So we have error that's reducible, and that's error related to our estimate of the function. We could have the world expert come in here and probably help us handle that. But the other part is going to be irreducible. What is irreducible error? Well, it's due to the fact that there are unmeasured variables. Maybe when it comes to predicting y, we didn't measure every one of the variables that would help us out. Or maybe we didn't measure all of the possible ranges and combinations of variables. There's the solution space has parts we have not sampled. And so even if we had the world expert in some type of machine learning technology show up, which would be fun to hang out, we could not, in fact, do a better job because the data doesn't support us doing a better job. That's a reducible error. Now, the concept of estimation error, it's the same as we had in geostatistics with the Kriging system. And so we have the expectation of the true value y minus the estimate of y, and we take that squared. And so if we were to expand that out and replace y hat with our estimator, our function plus our irreducible error, and we expand it out, we'd find that there's the two components. We have the irreducible component and we have the reducible component, which is related to our model. Now, more on estimation variance, or estimation error, I should say, shortly. Okay. Inference. Inference is a little less direct. There's value in just understanding the relationships between all the x's, understanding the influence of each one of them and how they interact with each other. Kind of the influences and interactions of each of these on y and, I'm writing inside the function, and each other. Just understanding the system, understanding the feature space and what it looks like, what's the shape of the possible solutions and so forth. That's pretty useful stuff. So which predictors are associated with the response, what data to collect, that'd be very useful. Not just building a model for prediction, again, an answer, but understanding which data would be most important to work with and what's the value of that information. That's very powerful. What data should we focus on? How can we simplify the model? Maybe we can have dimensional reduction. How do we communicate it? How do we tell people about the big hitters, as they say in industry? What's the relationship between each of the response and each predictor? Sense of the relationship, positive or negative, shape of the relationship, are there sweet spots? Are there spots where things tend to result in kind of a local high or something? Relationships may depend on the values of other predictors, so it can become kind of complicated. We can also step back and say, hey, can we model this thing linearly? If we can, life is much easier. And so maybe we're looking at the shape and assessing linearity of it in kind of multi-dimensions and assessing that. Or is it something we can work with? Some type of Gaussian approach would be easier, or lower parametric representations, dimensional reduction. So this is all around inference. Estimating f, our function, our machine that we want to make. Well, there's two different types of methods. There's parametric and non-parametric. We'll talk about parametric first. The parametric, you make a pretty strong assumption about the functional form or shape. Maybe you say it's a simple linear fit. And so then you use some type of model like this where you got your variables 1 through m. And for each one of them you have a coefficient. So you're basically fitting a hyperplane through your data set. That's a very strong assumption. You're saying this thing behaves linear with regard to y. We gain simplicity and also the advantage of only having to estimate a few parameters. So it's much easier to fit those few parameters. We don't need as much training data to fit it. And we can go ahead and then test our model and make sure that that model was reasonable given the parametric form that we have assumed. So this approach, parametric approach, by making that assumption up front, we limit the way our model can behave. But then it's much easier to infer the model because it has much fewer parameters. It has kind of a much simplified form to work with. Now there's always a risk that our estimate, our parametric estimate of the function, is quite different than the real one we should be working with. Then we get a very poor model. We get a poor result because we just are unable to fit the data. Now this is interesting because when you think about it, when we talked about machine learning in the definition, we suggested it's a method that can learn and tailor itself, adjust to different data sets. And so as we get to non-parametric, it becomes more powerful in its ability to adjust to data. But that's a preview. We'll get there right away. Linear model, an equation of first degree of any number of variables. Of course, that's wonderful. Requires only quadratic minimization to solve for the coefficients. It's just so easy to work with. We wish the world was linear. We wish the world was Gaussian, but often isn't. Model fitting, we apply the training data, and we can solve for least squares solution, coefficients, and so forth, but then we always have to be concerned about testing the model, and more on that later. Non-parametric methods. With a non-parametric method, you make no assumption about the functional form or shape. I do that because kind of there are parameters, but these methods are more flexible. Let's get into that. So we estimate the function that approaches the data without being too rough. We want something that kind of fits the data. We don't want to overfit, and we'll get into that. More flexibility to fit a variety of shapes of f. Less risk that our estimate of the function is just a poor fit because it's able to adjust the data. But it does not reduce the problem to estimating a small set of parameters. What's that mean? We typically need more data for an accurate estimate of the function. And we're at much greater risk of overfitting because we find ourselves in a situation where we may have few data relative to many parameters. In fact, I would suggest that nonparametric is really parameter rich from the standpoint that if you think about a decision tree, that's a nonparametric method, and we'll get into that in 2 lectures from now. That method really can be parameterized by a bunch of hierarchical binary segmentations that could be described as what's the order, what's the segmentation, and what's the average on each one of those nodes going forward. And so if you think about it, a decision tree, if you grow it really big, is going to be a lot of parameters for that model. And so that's why I say that it really is parameter rich. I'll give you an example of a neural net and show that. So often these methods, they really do lack a compact expression for the model, which kind of changes the portability. It's nice to have a function that you can use, and sometimes they can take some time to calculate if you're worried about speed. So let's talk about prediction accuracy versus model interpretability and explainability. Well, prediction accuracy, we can use estimation error, the expectation of the true value. In the case of training data, it would be the training data. In the case of testing data, it's the testing data, minus the model estimate, and we take the square of that over the and we take the expected over that. Well, in general, as prediction accuracy will improve as the complexity of the model increases, and I'll define complexity shortly. We'll find that if we have flexibility to fit the data, our model's very flexible, i.e. non-parametric, then we will typically have better prediction accuracy, unless your data matches the parametric form very well, of course. For example, a linear model may not fit the available data very well, and not as well as an artificial neural net if it's a very complicated nonlinear type form. Interpretability and explainability. There's a trade-off here. It's the ability to understand the model, how each predictor is associated with the response. For example, if we have a linear model, boy, it's so easy to understand. We can understand the influence of each one of the parameters. In fact, we could standardize the parameter and just look at the associated coefficients, and we could use that as an indicator of the importance of each of the parameters. Very simple to work with. But for an artificial neural net, it's more difficult. Now, this is something very interesting to me as an engineer and geoscientist type. I'm really interested in interpretability and explainability, right? But what you'll find is that in the machine learning community, you'll hear statements like this: as long as the complex models are properly validated, it may be improper to use a model that is built for interpretation rather than predictive performance. There you get to see a bit of the rub or the trade-off between this idea of accuracy versus interpretability and explainability. So a couple more comments around model accuracy. Well, first of all, method selection is very important. No one method performs well on all data sets. Imagine you could be working with some type of time series analysis and time series data set. You could be working with images. You could be working with sparsely sampled data in space, and you're trying to model between the data locations. Each one of these would require a dramatically different type of methodology in order to model. And so of course, your method selection is going to be based on your experience, understanding the data and the limitations, the strengths of each one of the methodologies. So we're going to try to measure the quality of our fit, and we'll use an equation like this, mean squared error, where we're just taking the average of the squared difference between the data values and the model, and you'll recognize immediately that that looks exactly like our concept of estimation error. And so we can go ahead and calculate this over the training data as we're building the model. We'll minimize this perhaps in order to get the best model fit to the training data. But the true challenge that we face is basically, how does our model behave when we make predictions outside the training data? Maybe a portion of our data set has been withheld, and used for testing. Maybe that's been done within some type of k-fold cross-validation approach or something like that. But in general, how does our model behave when we have to make estimates at locations that we did not train it in order to make an estimate? And so we'll be concerned about how it performs over locations that are within a training data set, or maybe when we apply the model in real life, we're concerned about how it will perform when we try to make estimates with it. Now, just to close up a couple loose ends here, if we talk about any type of prediction model, we would have either regression or classification. And the difference is simply that a regression model, the response variable is continuous, and a classification model would be one for which we have a categorical, or some termed in machine learning terminology as a qualitative variable. And so if we have a categorical output, that is known as classification. Now there's a complexity and flexibility decision or opportunity here. And so let's put some definition around that. Well, consider an example of multiple different models to try to predict y, and we have different models, functions or models f hat, which is our estimate of that model. And so one of them could be a very simple linear model where we just use one variable and we just have a linear weighting of that variable. It's a completely linear model with a constant and a slope in order to make a prediction of y. That's a first order linear model, very simple. We could also have a sixth order linear model using x at different powers with different coefficients to make a prediction. So in this case, we had to estimate 2 parameters, and we did not have that much flexibility. With this model, now we're estimating 7 parameters, and we have more flexibility. We're able to fit more complicated types of shapes in the data. Now let's think about what would it look like if we had, and we're jumping ahead here, we haven't really introduced the idea of neural nets yet, but imagine we have a neural net. So we have encoded the x with an indicator transform into zeros or ones based on which bin it falls into. Very much like we would do with a histogram. We could just encode the data based on which bin it falls into, and then we could feed that through our neural net. A neural net will be composed of a variety of different nodes. This will be a hidden layer in the middle here. There's functions that basically tell you that given what the input is in here, what should be transmitted to the next node, and what should be transmitted to the next node. And of course, those nodes will have some type of thresholds or some type of continuous functions that will translate that signal into something else that's then sent off. And you can see that this is a fully connected system. Everything is all connected with each other. Now imagine when you formulate that neural net, without getting into the details of neural nets, you would have to estimate specifically the form of each one of those transmissions. What's the specific thresholds? What are the forms of the functions, or whatever else related to the full combinatorial of node-on-node connections all the way through to this prediction of what's going on at y. This would be a lot of flexibility, but at the same time it would require a huge amount of parameters to be fit. And so we would expect that we need more data in order to do that, but we have a lot of flexibility available to us. So we can see that these 3 models would have dramatically different degrees of flexibility, quite inflexible, very flexible, and that in general it's related to the number of parameters that are being estimated to fit the model, to build the model. That's complexity. So there's a variety of different concepts that we can use to describe model complexity, number of features. If you have a lot more variables to work with, that could be considered a more complex model. It's higher dimensional and harder to look at and so forth. The number of terms and parameters. The idea that you could have one variable, but it could be first order or sixth order, as we showed before, or a neural net. And so those could be considered the complexity, the more terms or parameters that you're estimating the model. It can also be considered the expression of the model. Can the model be expressed as a compact equation, some polynomial regression that you can just write out on a short line with an equation, or is it a bunch of nested conditional statements that would be required to describe a decision tree? And so that could also be a concept of complexity. In this class, we'll consider complexity as the number of parameters in the model. And so the bigger the decision tree, the more complicated. the higher the power of the polynomial regression, the more complicated. And so that's how we'll use it, the concept of complexity. And so now we could also talk a little bit more about this idea of flexibility or complexity versus accuracy. And so, of course, as you increase the flexibility, you'll generally decrease the mean squared error in the training data set. You get more complexity, more flexibility, you're able to better fit the data, so you decrease the mismatch, the mean squared error at the data locations. But this may result in an increase of mean squared error with testing data. And so what happens is you become very well fit to the data, but you may not do very well with new data. So it's not generally a good idea to select the method only to minimize the training mean squared error. And so we could look at a function like this, where we have 2 through 30 or some other number indicating flexibility. So this could be like the number of terminal nodes in a decision tree, or something like that, number of parameters somehow. And what you'll find is that if you look at mean squared error, is that the training in general with greater flexibility and complexity, the mean squared error goes down. You do a better job. But when you do testing, you may find that in fact you're starting to lose the accuracy because your model is becoming overfit. So high flexibility, you minimize mean squared error, you likely are becoming overfit. And so let's make a couple of comments around overfit. Now I like this example. It's simple, it's a one-dimensional example. We have percentage finds, we have depth along a one-dimensional profile, and we're just trying to fit a function to it. And so we could fit a third-order polynomial, and we could calculate the confidence interval of this model. And the confidence interval is telling us about the certainty of the model, given the fact that we had to estimate it with limited data, and the behavior of the data in general. And so what you'll see is that we have this confidence interval. I believe it's the 95% confidence interval, excuse me. And this is the distribution of the residuals. How much mismatch do we have at the data locations? You take a fifth order, we start fitting the data even better, the residual distribution shrinks, the confidence interval starts to expand because we did not have any more data to inform a more complicated model with more parameters. What happens if we go to eighth order polynomial? Or we're basically one order away from perfectly fitting the data. The residual is shrinking to almost zero residual, no variance in the residual distribution anymore, and the model confidence intervals are off the plot. We're no longer confident at all in our model. Well, that's a great example of overfit. What's happening is we have an overly complicated model trying to explain the idiosyncrasies of the data and capturing data and noise, error in the data, rather than things that are meaningful. We have more parameters than can be justified with available data. The result is we have very high error away from the data, or if we use new data. But this results in a low residual variance. With regard to the training data, it looks like we are doing great. We have a high R-squared. We're describing all the variance, but we're only accurate at the data locations. We claim that we know more than we actually do, and that's overfitting. It's dangerous. Let's just cover this concept of bias and variance trade-off. And this is a very important concept. And so if we take another look at the idea of the estimation error, and we are also represented as the mean squared error, and we look at it specifically with regard to the locations that are not in the training set. We're dealing with the locations that are in the testing data set, not used to build the model. That's why we show them as not. They're not in the training data set. Okay, if we look at them, we can decompose this equation into three components. And so these components will include the model variance. They include the irreducible error over here, and they include the model bias. And so model variance is the variance if we had estimated the model with a different training data set. That's the sensitivity of our model to changing the input data that we use for training. Model bias, it's the error due to the fact that we have an approximation. A simpler model has trouble fitting all of the features in the data, so to have higher bias. While model variance, simpler models are more robust. They're not as sensitive to the data. They have lower model variance. Irreducible error, well, we can't get rid of that as we discussed before. That's due to the fact we haven't sampled all the variables. We haven't sampled the entire solution space or feature space, and so we can't fix that with modeling. So if we look at these functions or plots, directly from the James and All book, which I appreciate this very much. We got degree of flexibility going from simple to complicated. And so what we'll see is that in general, that model bias goes down as you get more complicated. You see that because we're able to better fit the data, the features in data. We'll find that model variance goes up because with more complexity, our model becomes more sensitive. And we got irreducible error right here, which will be just constant. We can't get away from irreducible error. It doesn't matter about complexity, it's constant. Add those three up, and we get this red line. This red line is the expected test mean squared error in using the model. And so what you'll find from this is something really important, and that is, at times the optimum amount of flexibility and complexity is not on the right-hand side. It may be somewhere on the more simple side, or it may be more complicated. It will depend on the problem. But we should be cognizant of the fact that there is a trade-off between model variance, model bias, and we have to balance the two. So I hope that this was a useful introduction to some concepts in machine learning. With these concepts, we can start diving into some machine learning methodologies. And so these methods will specifically help you with model inference and prediction. And you'll be able to work with complicated data sets. It'll increase your ability to do big data analytics, to be able to work with those large data sets and to detect patterns and so forth, all part of that. Remember, it's in our business to win. And those who win, when I first started my career, it was always those who have the best data will win. I think it's those who use the data best will win. Well, welcome. You're in the fourth paradigm of scientific discovery. The third paradigm was all of that engineering-based approaches and using experimentation, figuring out the physical relationships and so forth. Nope, we're now in the data-driven type of discovery period. So, welcome to that paradigm. I think that we will probably see a lot of these methods grow and become more important, and it's good for us as engineers and geoscientists to know about them. Of course, there's going to be tons of opportunities with areas where we collect very dense data. We'll definitely need these technologies, and including a lot of different areas we work in. We're going to start next lecture with unsupervised methodologies for dimensional reduction. We'll get into principal components analysis. We're going to show that based on an unconventional data set, and we'll show some examples in R and I believe in Python. So I hope that this summary was useful to you. Once again, here at the very end of this, what turned out to be a longer lecture than I hoped, I want to once again acknowledge that of course, I'm very interested in the ways that we can use machine learning within our expertise, our fields, to be better engineers and geoscientists. There are lots of really good resources that I'll be showing as we go along here. I myself am also growing in this field, so I do not want to falsely advertise myself as one of the leading experts in this field, but I'm one who am trying to also learn too. Anyway, I hope this is helpful. I'm easy to reach. I'm Michael Pyrcz, a professor here at University of Texas at Austin, and I am also the Geostats guy on Twitter, and I'm easy to find if you have any questions or comments. All right, thank you very much.